Hello, everyone. So here is our final topic to cover, but this will take several days because there's so many different ways to generate a volume of a solid. Now, if the solid is a nice geometric solid, we're able to use a formula to find the volume of that. But most cases, that's not going to happen, so this is why we need calculus. So just to go over the basics of volumes again. What volume is just the amount of space inside of an object and measured in cubic units now, so we have to be aware of that. And any kind of geometric solid, the formula for volume is just the area of the base, which we denote with a capital B, times the height. A very simple, common example here is just a volume of a cylinder. The area of the base it's the area of a circle, so it's pi r squared times our height. So the volume of a cylinder is pi r squared times our height. So again, if we generate a nice geometric solid, we could use a geometric formula for finding volume, and then other cases we can just use calculus. And in those cases, it's tied in nicely to what we were finding the area between curves sometimes. All right, so let's take a look at this lesson. The first example is just one on creating. Others will come from a gift, a worksheet 7.3. The idea is not to give you too many problems to do, but just a nice variety to give you an overall basic understanding of how to use calculus to find the volume of a solid. All right, so we're going to find the volume of a solid that's generated by rotating the line y equals x about the x-axis from x equals 0 to x equals 3. So first what we want to do, and if you have graph paper, I prefer that you do this on graph paper to just be more accurate. We want to graph the line y equals x, and again, just from 0 to 3. And we'll draw that in. All right, so essentially what we're doing is we are going to find like the area here, but we're rotating it. So what's going to happen is if we start to rotate this line, it gets reflected. So imagine that this just starts revolving about the x-axis here, so that the x-axis is the center. Well, what's happening now is as soon as this gets reflected over the line, over the x-axis, then we have the same result over here. And I'm just going to try to draw this as best I can. I have a nice little YouTube video clip of an animation of something being rotated and to generate a solid figure here. So just imagine like this point is just getting rotated this way. Use a different color here. Down to here. So we get a nice circular base here. So I could do this with a variety of points, but just showing this as well. So we get to end up seeing a three-dimensional figure form by rotating this. So let me go to the clip real quick. All right, so again, imagine and we could create a triangle if I shaded the area in, but this is just to show if we take something that's two-dimensional and start to rotate it or revolve it about a certain line, this is what happens. So here it is just going around and around, and then if we kind of mark all of that, we get a nice three-dimensional figure. So you can see as this keeps revolving, we have this three-dimensional figure here. So that's what I kind of wanted to show you in a better animation than what I can do. All right, so that's what's happening here. Now, if you notice, this is a nice three-dimensional or geometric solid that we're looking at, and we do have a formula for this. So as we keep revolving this, this is just giving us the shape of a cone. But before I talk about that, so there's going to be two ways to do this. I'll show you the calculus way, and then we could just go back to the formula for volume of a cone. But each red circle here, I'm going to call a slice. So each slice is a circle. And if I were to, going back to, remember how we found the area, we took a lot of rectangles and added up the areas of all those rectangles. We're going to do the same thing here. If we found the area of each little circular slice and then added those together, we will get the volume. So we call this volume by slicing or by discs. So we're making little circular discs and then we add those up. So the area of each slice is pi r squared. Then the volume is going to be the sum, so the integral as we go from x equals 0 to x equals 3 of each area of the slices here. So then we would say, in this case, each radius starts from the middle here and goes up. So I'm not using an r, but because this is the line y equals x, each length here is just x units up. So however far we go over x units up as well. So instead of pi r squared, I'm going to say pi x squared and then dx. So again, the pi x squared is the area of each slice. This dx is the thickness of each slice. Think of like a thickness of a dime, thickness of a nickel, of a quarter. If we were to stack those up, that would be the thickness of each slice, and then each slice would be the coin itself. So just to finish this using calculus here, so we would just get, we could take the pi out in front if you want, and then say the integral just from 0 to 3 of x squared dx. One thing you will notice with these is the integrals are a lot simpler than what we've been working with areas in the past. So the actual math involved, the calculus by hand that's involved, isn't going to be that crazy. So we'll just say it's going to be pi times x cubed over 3 from 0 to 3. So we're going to get 27 over 3. We're going to get 9 pi, really minus a 0, so we get 9 pi cubic units. And that was using calculus. Now because this is a cone, the formula for volume of a cone is that of a cylinder, but we're taking some off because it comes to a point here. So it's actually a third of this. So it's going to be 1/3 pi r squared times our height. So we get 1/3 pi. Again, our radius here is going to be 3 if we're looking at the cone, because we take the area of the base. So looking at this would be at the very end, would go up to 3. So we're going to say 3 squared. And then our height is also 3. Looking at it this way, this would be the height of the cone. So again, we're going to end up with 9 pi cubic units. But we're not always going to be able to use a formula. Just in this case, I wanted to start off with a very simple shape. We were able to look at this 2 different ways, but know that they came out to the same answer. But what I want you to focus on is the calculus version of figuring this out. All right, so our next 2 examples are coming from the gift 7-3. So please pause the video, read this over, go ahead and graph these 3 lines, or the parabola and the 2 other lines rather. Okay, so I numbered my axes. I kind of spread them out a little bit, spaced them out, just to get a better view of this. So the parabola, 1/2 x squared, even though we're just going from x equals 1 to x equals 3, I'll cut that off a little bit later. But here are some points that we're taking a look at, and we get a nice parabolic curve this way. All right, but we're going to cut this off from x equals 1 to x equals 3. So I'm going to go ahead and just make dotted lines, dashed lines here, because we just want to stop it. We're just looking at the area for right now that we're going to revolve. So as I go to reflect this, because this is rotating again about the x-axis. So if I have this point here at 1, 1/2, then I'll have 1, -1/2. And then at 2, 2, we'll have 2, -2. And then 3, we have 4.5 really. So 3 and then -4.5. So it will reflect this way. I'll just kind of start it from here. All right, so what's happening is we start to rotate it. So we're going to get our circular slices like here, here, and then even here. Try to draw a circle as best you can. But what this is no longer like a cone like in the last example. It looks kind of more like maybe a lampshade or something, and there is no formula for volume of a lampshade. So again, what we need to understand is each circle, each slice is a circle rather. So then the area of each circle is going to be, again, pi r squared. But in this case, when we go to look at each radius is going to have a length that matches this function that's right here. So this is y equals 1/2 x squared. So now this becomes pi. Our radius here is our y value, which is 1/2 x squared squared. So now this simply becomes 1/4 pi x to the 4th. So that is our area, and our volume is going to be the integral from x equals 1 to x equals 3 of our, technically we could put the 1/4, I'll put it in here first that we could say 1/4 pi x to the 4th. So that's the area of each slice times the thickness of each slice, which is dx. And then we could maybe make this a little easier. We could put the 1/4 pi or pi over 4 out in front, and then times the integral of 1 to 3 of x to the 4th dx. And now this becomes 1/4 pi times x to the 5th over 5 of 1 to 3. So we get 1/4 pi. 3 to the 5th will actually be 243 over 5 minus 1/5. So we get 1/4 pi times 242 over 5. 242 pi over 20, which becomes 121 pi over 10 cubic units. All right, so again, the idea here is to first figure out what shape each slice is, and to begin with, each slice here is going to be a circle. We're going to get into different cases down the road where each slice might be a slightly different shape here. So we take the area of each slice and then we multiply it by the thickness. So this is very important right here, just off to the side before we set up the integral for volume, that we figure out how to write our radius. That's the part that's going to change, and it's all based on the graph that we're looking at. All right, so let's try one more example. This is number 2 off of the gift that I'll give you here shortly. We want to find the volume generated by rotating again. Well, this time it's about the y-axis, the region bounded by the graph of y equals x squared, the y-axis and the lines y equals 1 and y equals 9/2. So right now, pause the video, go ahead and graph y equals x squared. Now, because we're rotating about the y-axis, you're going to draw this on both sides. You could just draw the right side of 0, and then it will reflect over the y-axis. Okay, so what I have graphed so far is just the right side of our parabola for right now, just to show when we go to reflect it to the other side. Then I also have the 2 horizontal lines for y equals 1 and then y equals 9/2 or 4.5 here. So because I'm rotating this about the y-axis here, I just need to reflect this over to the other side. And then draw it this way as well. Okay, so the part where we're going to see the circular disc is going to start at the very top. And then we could just draw a series of circular discs throughout just to show what this would look like. So we can get an idea of what the solid will look like here. And again, we're not going to go below the line y equals 1. So we're just staying between y equals 1 to y equals 4.5 here. But this is the shape we're getting. So again, what we want to say is each slice is a circle. The area of each circle is going to be pi r squared. But notice in this case, our radius is going horizontally here. So remember when we looked at like with respect to y, that's what we're looking at here. So we have to go over the x value. So in this case, x is going to equal if y is equal to x squared, x is going to equal the square root of y. And I just need to keep it a positive because I'm going over just to the right here. So each radius is going to equal the square root of y units. So this is going to become pi r squared, which becomes pi times the square root of y squared, which is just pi times y. So when we go to write our volume, that's going to be the integral. Now, this is with respect to y, so it's going to be y equals 1 to y equals 9/2 of pi y dy. And we'll go ahead and finish this. So we could just say that this will become pi times y squared over 2, and then evaluate very carefully from 1 to 9/2. So we're going to get pi times 9/2 squared over 2 minus pi times, that'll just become 1/2, so we just say pi over 2. So 9/2 is going to be 81/4 over 2. We'll put the pi after it, minus pi over 2. So this is taking 81/4 and dividing it by 2 or multiplying it by 1/2. So we actually get 81/8. And then we could say this becomes 4 pi over 8. So then we get 77 pi 8 cubic units. All right, so I'm going to give you guys just a few problems to do off of GIF 7.3. Maybe in the next day or two, I'll have the answers up just so you could check. So it's nothing I'm going to collect here. I just want you to work on them to understand them. Like I said in the post, the announcements I made, I'm going to give a final quizzes over everything in this section by the end of next week. So please let me know if you have any questions. Make sure that you're checking your solutions when I post them as well. Take care, guys.